All right, welcome back. I have decided to close this section on fractions by looking at a few questions from the previous two video lectures. So in this section, we'll look at a selected number of questions from the eWorkbook on fractions. And hopefully this will help you solve the remaining questions. All right. So we'll start by answering questions from page 4, the packet or the set B, and we'll be looking at question number 4. Question number 4 says, I hope you can see this clearly. The question says that a piece of paper is 7/1000 centimeters thick. How many sheets of paper will it take to make a stack that is 5 centimeters high? Okay, so we know the thickness of one paper. We want to know how many of these papers we'll need to make a stack like this, which is 5 centimeters thick. All right, so how do we proceed with this? Should not be very difficult. One paper has a thickness of 7/1000 of a centimeter. What we'll do is we'll assume that there are n number of papers in order to make 5 centimeters. So if 1 centimeter has got this thickness, then this thickness multiplied by the number of pieces of paper should give us 5 centimeters thickness. So we can write then 7 out of 1000, the thickness of one paper multiplied by the number of papers, n, must be 5 centimeters thick. All we have to do now is to divide both sides of this equation by 7 out of 1000. So you can already see that we end up with a complex fraction, because we will have n equals 5, because we've divided both sides by 7 over 1000, and so this is going to be over 1000 like that. So we have a complex fraction. This is the same as simply flipping the denominator and multiplying by 5. So this is going to be 5 multiplied by 1000 over 7. So this, we are reasoning, we are using our understanding of complex fractions to simplify this. And make use of a calculator. We rearrange that so that you make n the subject of the formula by dividing both sides by 7 over 1000. We end up with that. And if you use your calculator to work out that, we should get that we need approximately 714 pieces of paper to make a height of 5 centimeters. I hope that is clear. Let's go to the next question. So this was question 4 of packet B or set B on page 4 of the eWorkbook. All right, let's next look at the next one. I have also chosen to solve the question on page 5 from packet C, and this time we are solving question number 4. And the question says, when a sound source such as an ambulance travels towards you, the sound you hear as it approaches you is normally different from the sound you hear when it is receding from you. So as it's coming, you hear a sound of lower frequency, and when it passes, you hear sound of higher frequency. That behavior or that phenomena is called Doppler effect. And we are being told that the frequency, or the observed frequency, the frequency you hear as the ambulance is approaching you, is given by this formula here, where A is the actual frequency of the sound being produced by the siren in the ambulance, and S is the speed with which the ambulance is traveling. So in short, with all that information being given, this is from physics, the question is simply to make this simpler. All right, simplify this expression. All right, so in short, we are just being asked to simplify the expression that. So how do we go about this? We've learned how to simplify complex expressions. We need to deal with the denominator. The first thing we need to do is to turn that into 1 out of 1 so that it's also a fraction, so that the denominator of the complex fraction is made up of 2 fractions, like that. Okay, and now we need to deal with that denominator there. All right, the way we deal with the denominator, which is the difference between 2 fractions, is just take that 770, multiply by 1, and then we subtract 1 times s, and then everything divided by the product of the denominators, like this. We need to deal with that. So we'll end up with 770 times 1, which is 770, minus s, everything divided by the product of the denominator 1 times 770, and that's what we have. And now we have a divided by another fraction. So all we have to do is to take the a, instead of divide, we multiply by the flipped denominator there, or the divisor, and we end up with a times 770, everything divided by 770. All right, so a divide by, so this is the divide sign here for this line. So we are dividing by that denominator there. And so we are going to change that to multiplication sign and flip this, and we end up with a times 770 divided by 770 minus s, like that. Okay, so that's what we end up with. And when we simplify that, we get 770a over 770 minus s. So I need you to get used to simplifying fractions, complex fractions like this, because you will meet it a lot. Here is an example where you meet it in physics, and you will meet complex fractions in mathematics, and you'll meet complex fractions in chemistry, and so on, as well as in economics. All right, let's look at the next question. So that's the simplified form of the Doppler effect formula used in physics. Next question. I picked the next question from page 6, packet D, and this time it was question number 3. All right, so a number sequence given by u1, u2, u3, and so on, un plus 1, and so on, in which the ratio r between any 2 successive terms is the same, is called a geometric sequence. I will explain this as we go, of course, in case you've not met this before. If the next term is less than the current term, in every case, then we can find the sum of all the terms in the series. That means we can find the infinite sum using the formula S is u1 over 1 minus r, where u1 is the first term, the term that comes first, and r is called the common ratio. Okay? Use that information to show that 7 over 10 plus 7 over 100 plus 7 over 1000 and so on to infinity, this is actually a recurring decimal, can be expressed as a fraction, which is to say is a rational number. So express the sum of this sequence all the way to infinity as a fraction. Okay, that's the equivalent to saying change the recurring decimal 0.77777 into a fraction. So this is a second way of converting a recurring decimal into a fraction. So how do we go about this? Before we go on, I want to explain what this question is really saying for those who've not discussed sequences and series. Okay, so what do we mean by a geometric sequence or a geometric series? All right, so here is a sequence of numbers and I have added them. So the correct word actually to use is a geometric series. So when you add elements in the sequence, we call it a series. We no longer call it a sequence. So here we go. So I have a number 2 and I'm going to add 6. Then I'm going to add 18 and so on. Now looking at this sequence of numbers, there is a pattern. All right, and there's a pattern that tells us that this is a geometric series or a geometric sequence. All right, now if we can see first of all that the sequence, the numbers in the sequence are getting larger and larger. So the first one is 2, the next one is 6, so obviously that has increased. So 2 and 6 are called consecutive terms, this being the present term and this being the next term. Between 6 and 18, this is the present term and that is the next term. So this would be un and this will be un plus 1 and so on. You can pause the video and predict what number comes next. But otherwise, we see that the term's getting bigger, so we can conclude that the current term is, if this is our current term, then the current term is always less than the next term. If this is our current term, then the next term is bigger. So we say that the current term is always less than the next term. So the n plus 1 term means the next term, the immediate next term, okay? In such a case, we refer to this as a diverging geometric sequence or a diverging geometric series. A geometric series is also called a geometric progression, so hence GP, but that should not worry you much, okay? Now, when we have a GP such as this, we can always find the next term because there is a relationship between two consecutive terms. So there is a relationship between 2 and 6, which is the same as the relationship between 6 and 18, okay? That relationship is the common ratio. So if I take the next term and divide by the current term, I get something called the common ratio. Why we call it the common ratio? Because we can find that same number using these two terms, or these two terms, or the next two terms, and so on. So if this is our un, then this is our un plus 1. If this is our un, then this is our un plus 1. So given a sequence like this, if we can find a common ratio, that is 6 divided by 2, and we find that is the same as 18 divided by 6, then this is a GP. All right, so the common ratio is the ratio of the next term to the current term. All right, the ratio of the next term to our current term. So in this case, you can see that our common ratio is going to be 3. And in fact, we can use the knowledge of that common ratio to find the next term. Because if we know that r there, then we know if I take 2 and multiply by r, I should get the next term. So 2 times 3 should give me 6. 6 times 3 should give me 18. And so 18 times 3 should give me the next term, which if you have tried to find it, should be 54. Okay? So this is a diverging sequence or a diverging series. A diverging geometric series. Okay? Right. Here is another one. I start with 64. By the way, the 2 there is called the first term and is usually represented by u1. So in place of un, the n is 1 to indicate that it is the first term. All right, so let's go to the next sequence of numbers. So I start with 64, which is my first term. The next term there is going to be 32, followed by 16, and so on. Now you can see that in this case, the numbers are getting smaller. So the terms are getting smaller and smaller. When the terms are getting smaller like this, we see that the current term is always bigger than the next term. The current term, so if my current term is 64, then 64 is always greater than 32. If my current term is 32, then 32 is always greater than 16, and so on. So I know that the next term should be smaller than 16, and the following term should be smaller than this term. Take a few seconds, you can pause the video and predict which numbers come next. The next 3 numbers that we get in this sequence, that should not be a difficult challenge. All right, in this case, if the numbers are getting smaller, then we refer to this as a converging geometric sequence or a converging geometric series if we are adding the terms like that. Okay? Now, using the same idea, how do we find the common ratio? The common ratio is the next term divide by the current term, and if you check here, you should be able to see that the common ratio is 32 divided by 64, which should also be the same as 16 divided by 32, which should be the same as what we have here, divided by 16, and so on. And if you check that carefully, you should see that it is actually a half. Okay, so the common ratio for this particular sequence is actually a half. Another thing that we could find, in the case where the terms are getting smaller, in the case of a converging sequence, another thing, so this is the case of a converging, this means a converging sequence. So in the case of a converging sequence, the other thing we could find is the sum of all the terms to infinity. So if you can go as far as you like. If we found all the terms from 64 all the way to infinity, it is possible to find those the sum of those terms using the formula S for sum is equal to U1, where U1 is the first term, in this case it's 64, divide by 1 minus R, and our R is a half. So you can check quickly what the sum of all these numbers would be. If we added them all the way to infinity, the sum would be S equal our first term from here. Our first term is 64, so I'll say 64 divide by 1 minus our common ratio, and our common ratio there you can see is a half. We found it, that is a half. All right, you can see we have a complex fraction. So this is 64 divided by 1/2, which is in fact 64 times 2 over 1. And that tells me that the sum of all these numbers, I don't need to know all of them, but if it is a GP and I know at least 3, this 3 will help me confirm that there is a common ratio of a half. And if that's the case and I have the first term, that information is enough for me to find the sum of all of them without actually having to list them out or to add them numerically. All right, so you can see this gives me 100, I believe 128. So if I added all these numbers all the way to infinity, I will get 128, like that. Right, we'll move on. Okay, and so I've used those few minutes to try and explain what a geometric sequence looks like. So now let's look at the question at hand, question 3 in this packet D on page 6. So the sum for this one is 128. Now let's move on and look at the one we've been given. Now you can see this is the question we're being given, and we're being told to show that this adds up to some value A over B, and we will find out what A and B are. Okay? So if you look at this sequence or a series carefully, you should notice that it is a GP. If we can show that this term here, 7 over 100 divided by 7 over 10, if we can show that that ratio is the same as 7 over 1000 divided by 7 over 100, if we can show that is the case, then this is a geometric sequence. Okay? So you can see that 7 divided by 100, so 7 over 100 divided by 7 over 10 is 7 over 100 multiplied by 10 over 7. Our knowledge of application of fractions, and the 7 cancels with the 7, and 10 divided by 100 is 1 over 10. So this is indicating that the ratio is 1 over 10. Now let's confirm that that's the same if we take this divide by that. So of course 7 divided by 1000, okay, 7 over 1000, and now we want to divide by that, which is 7 over 100. This is the same as 7 over 1000 multiplied by 100 over 7, and this cancels with that, and we can see these 2 zeros goes with those 2 zeros, and this is also giving me 1 over 10. So we have the ratio of this 2 is the same as the ratio of this 2, so we have a common ratio. And when we have a common ratio like that, then we can conclude that this is a geometric sequence, and if it's a geometric sequence or a geometric series, then this formula here can be used to find the sum of all of them all the way to infinity. All this added all the way to infinity. Okay, let's see that. So the common ratio R is 7 over 100 divided by 7 over 10, all right, which we can write as, we already found that to be 1 over 10. So the common ratio for this is 1 over 10, the GP. But we also know the first term because we are looking for the first term and the common ratio. So we know value of R and we know the first term is 7 out of 10. Okay, so we substitute this into this formula and we will say that the sum of all the terms, also called the sum to infinity, is given by the first term there at the top, divide by 1 minus the common ratio, which is 1 over 10 there. And if we do that, subtract, that is 1 over 1 or 10 over 10 if you like. That should give us 9 over 10 in the denominator. So we can write this as 7 over 10 in the numerator, change that to 1 over 1, use our addition or subtraction of fractions at the bottom there in the denominator, and we end up with 7 over 10 divide by 9 over 10. Please confirm that you're okay with that. And then if we flip the denominator, we have 7 over 10 times 10 over 9. Okay, the 10 and the 10 cancels, this and this will cancel, and we remain with, please just confirm, so the 10 and the 10 cancels and we are left with 7 over 9, like that. Okay, and so the sum of all this is 7 over 9. So the value of A is 7 and the value of B is 9. We conclude that the sum of that recurring decimal, by the way, this is a recurring decimal which is also the same as, this is 0.777 recurring, like that. All right, so the recurring, and you can try to use our method of looking for changing a recurring decimal into a fraction. Confirm that if you did that here, you would get 7 out of 9. Okay? Use the method that we've used in video number 2, lesson 2, to show that the recurring decimal 0.777 can convert to a fraction as 7 out of 9. Okay? That is how you answer this question. Let's go to the next one, assuming that this is okay. If you find this still difficult, don't hesitate to ask. As far as sequences and series is concerned, this is a topic we will be looking at in the future, so do not worry so much about it. Our interest here is working with the fractions. All right, let's go to the next one then. This is on page 7, packet E, packet of questions E, and we are only looking at question 3A. So there are a number of questions there, but we will only pick one of them, which is question 3A, and I think this relates to complex fractions. Yes, so we are asked to solve the equation 12x power negative 1 divided by 4x power negative 1 minus 1, everything minus 6 equals 0. The first thing I want you to remember is that x power negative 1 is the same as 1 over x, like this. Okay, so x to the power of negative 1 is the same thing as 1 over x. And so I can now write this as 12 times 1 over x, and this as 4 times 1 over x, like this. All right, so we have 12 times 1 over x, which is also 12 over x. And 4 times 1 over x is also 4 over x. So we can rearrange that like that. Okay, now I have also expressed 1 as 1 over 1 so that I have a fraction like that. And now I can deal with that denominator there. I have to fix that first, and I can see that it is 4 minus x. I'm multiplying them. So 1 times 4, 1 times 4, subtract x times 1. divide everything by x times 1, okay? Product of the denominators. Right, if I do that, I end up with 12 over x, and then I have x here, so 1 times 4. So I have, in the top, I have 12 over x, everything divided by. Now in the denominator, I have 1 times 4, which is 4, minus x times 1 is x, and everything divided by the product of the denominators, which is x, like that. So I'm only dealing with this part yet. So if I rewrite that, I get, so this is what I've just found. And now the next thing is, of course, to solve this complex part. Ignore the minus 6 yet. All right? So what does that give me? So I have 12 over x divided by 4 minus x over x. And I can flip this, so I have 12 over x times x over 4 minus x. This is x. This is x. Okay? And of course, this will cancel with that, and I'm left with 12 over 4 minus x, as you will see shortly. So I hope you can see this. Right? All right. So the next thing is writing that in that format. So I've already flipped it. You can see you can flip. So this goes up and that goes down, and now we multiply. And we can simplify these two. X cancels with x there, so that x cancels with that x, and we are left with 12 over 4 minus x. So we can write 12 over 4 minus x minus 6 over 1. Now I'm bringing the 6 into play. It is 6, so I can just put it as over 1. All right. Next is, because this is minus, I can move it to the other side of the equal sign. If I do that, I end up with that expression there. And now I can use the principle of cross multiplication that we've discussed in the first video. Okay, video number 01, or part 1 of the series on fractions. Please look at that. We've looked at the idea of cross multiplication. So here all we have to do is cross multiply. 12 times 1 must be equal to 6 times this bracket, like this. So by cross multiplication, we're going to end up with 6 times 4 minus x into bracket must be equal to 1 times 12, which is just 12. And if you open that bracket, 6 times 4 is 24. 6 times x is minus 6x. So 24 minus 6x must be equal to 12. And if we rearrange that, we can rearrange it by moving the negative 6x to the right-hand side and moving the 12 to the left-hand side. 24 minus 12 must be equal to 6x. So 6x must be 12. And x, if we divide both sides by 6, x will be equal to 2. I hope this makes sense. And so we have solved that equation. Some people might look at that and think it is very, very difficult. But once you change it like this and use your understanding of complex fractions, then this should not be very difficult. Try the other questions in the same pack on page 7 and see that you feel comfortable with this kind of questions. Okay, I believe this is going to be the last one. This is on page 8 and packet F, question number 2D. All right, I think this is on polynomials. All right, simplify the rational expression. So this is a polynomial long division. It's a part of the last discussion on video number 2. Okay, and we are told to simplify. So we are basically dividing the cubic polynomial by the linear polynomial. Okay, so it's like you divide regular numbers. I can put regular number on the side like this. If somebody say divide 352 divide by, let's say, 8, then what we normally do is that put the 8 out, the divisor out, and the number being divided inside 352, like that. and then we ask ourselves, 8 does not go into 3, so we must take 35. 8 goes into 35 4 times to give us 32. So I'll write it goes 4 times. Then I say 4 times 8 is 32. So I write 32 here. And I subtract. Okay, so 35 minus 32 is 3. And then I bring down my 2 there and I have 32. And 8 goes into 32 4 times. And 4 times 8 is 32. And if I subtract, there is no remainder. And so I can say that 352 divided by 8 is actually 44, like that. So I want to use this same approach in dividing these two polynomials. Okay, I'm going to have to remove it. Please take a look at the process as we go through it. I'm hoping that everyone knows how to do this. But then we have to apply the same technique into this. Okay, so this is the divisor. It will go out, and then the number being divided, in this case an algebraic expression, goes inside, like that. So the divisor is outside and we have our number inside. So the first thing we want to say is this is how we go about this. I've explained this in video number 2. So this is how we go about this. On the way forward, we only think about x. On the way backwards, we think about both, like this. So we take x and we ask just the same way that we ask how many times 8 goes into 35. So x goes into x cubed how many times? In other words, what do I multiply by x to get x cubed? Well, the answer is x squared. So x times x squared will give me x cubed. All right, so another way of saying this is that x goes into x cubed x squared times. So we write x squared up there. And now we multiply back. Now on the way back, we multiply x, but we also multiply -2. So we'll say x squared times x, that should be x cubed, and we write it there. In that case, we got 32 because we had 4, and then 4 multiplied by 8 was 32. All right? And x squared multiplied by -2 is -2x squared. Then what we need to do is now subtract the same way we took 35 and subtracted 32. So we draw the line and subtract. X cubed minus x cubed is 0. -4x squared minus negative. So -4x squared minus -2x squared. So minus negative becomes plus. So it's like minus 4x squared plus 2x squared. That is going to be -2x squared. All right. And now we drop the next number the same way we dropped, I think it was 2. So now we drop the next two numbers here. So x and 6 there, we drop them down. Okay. And we start again. X goes into -2x squared. In other words, what do I multiply by x to get -2x squared? That is going to be minus 2x. So we write minus 2x there and multiply back. -2x times x is going to give me -2x squared. And -2x multiplied by 2 is going to give me positive 4x. Once again, I subtract like that. This minus that is 0. X minus 4x is going to be -3x. And now I bring down my 6 like that. Okay, we repeat the process. X goes into -3x, -3x times. In other words, what do I multiply by x to get -3x? It is -3. And now -3 multiplied by x gives me -3x, and -3 multiplied by -2 gives me positive 6. All right, and then I subtract and I can see that there is no remainder. So this minus that is 0 and this minus that is 0. So there is a remainder of 0. And so we can conclude that this number divided by this expression divided by this expression is this thing here at the top, just like we did before. Okay? So that is going to be our answer, and we can conclude that dividing those two polynomials will give me x squared minus 2x minus 3. That is the answer. Okay? Use the same technique to answer the other questions. We did D. I think there are still others in there for you to solve. Please check them out, and let's see what you come up with. Don't forget to notify me if you have any difficulties solving this type of question. Okay? All right. I think this brings us to the end of the discussion on fractions, unless somebody asks a question, a particular question, and we have to include it in here. This brings us to the end of the discussion on fractions, and we will move to the next discussion in the next video. But before I go on, I have included the workbook, the eWorkbook, and just under the timestamp, you will find that there is an additional question that we give MYP5 student, and this is an investigative task that falls under criteria B of the IB assessment criteria. So this is on page 9. It is suitable for both MYP4 and MYP5, but the level of difficulties as you go through the different parts of the question increases, so that at some point only MYP5 students will be able to proceed. Okay? I would like you to try that question. For my student, this is going to be one of your criteria B tasks. So you may start taking a look at it and see how you would solve it. All right? Others can still try it out, and let me see what you get. If you need clarification or you need support through that particular question, do let me know. All right? Otherwise, thank you very much for watching. If you're seeing this for the first time, or if you forgot to subscribe, please take the opportunity to subscribe to the channel and hit the and like the video as well. Share widely with other students who may find the material useful, and I will see you in the next video. Thank you very much, and bye.